Alright, so in this chapter we are going to talk about oscillations. So oscillations are everywhere in the world around us. You have oscillations at the level of atoms, and you can also have oscillations in stars, very, very large systems. So why do you have oscillations? Well, any kind of oscillating system uh, is characterized by restoring force or torque. So let me just give you an example of that. So let's take the simplest possible example of an oscillation, which is the spring mass system. And since that's one of the easiest systems, we are going to focus on that a lot in this chapter. So the spring mass system consists of a spring which is connected to a mass, and the mass is sitting on an absolutely frictionless surface. What would happen if you displace this mass a little bit? So if you move this mass a little bit to the right, maybe move it over here, let's call this point x equals 0, and let's call this point x. So you've stretched the spring by an amount x, and let the mass go. So what's going to happen is that the mass is going to feel a force to the left, which will try to bring it back to x equals 0. You might recognize this force back from chapter 11. We call this kind of force, which tends to bring a system back towards equilibrium, as a restoring force. So when you displace this mass, so originally the mass was in equilibrium when the spring was not stretched, all the forces on it were 0. But when you stretched it, there was a force on it which tends to bring it back to the equilibrium point. So you can clearly see that there is a restoring force in this case. What's going to happen next if you let it go? So the mass will come back to x equals 0. The restoring force will vanish at x equals 0, because you know that the spring is not stretched, so there is no reason for the spring to exert any force at that point. However, the mass is not going to stop at x equals 0. It will, as a result of inertia, it will continue moving and maybe move somewhere over here. To the other side. At that point, the spring will be squeezed, and so once again you're going to have a restoring force, but to the right. And that will push the mass back towards x equals 0, but it will again have a velocity. And so it won't stop at x equals 0, it will go over to the other side. And so the system will just keep oscillating back and forth. If there is no friction, then this oscillation will just continue forever. Okay, so you can see that any kind of periodic motion or oscillation needs to have a restoring force. It could also be a restoring torque, not necessarily a restoring force. And I can show you an example of a restoring torque. Okay, consider a pendulum. A simple pendulum just consists of a massless string with a point mass attached at the other end. Point mass just means that the mass doesn't have any appreciable spatial extent, and the string is also very, very light. Okay, so if you just let this mass hang, then it's in equilibrium. The system is in equilibrium. But suppose you displace the mass by a certain angle. Now it's no longer in equilibrium, because you have the gravitational force acting down like this. And as you can see, the gravitational force exerts a torque about the pivot point, right? You can easily find the torque of the gravitational force about the pivot point. And so this torque will try to rotate the pendulum back to its equilibrium position, right? So this is an example of a restoring torque. And the same thing will happen. So once the torque, the torque brings the pendulum back to its equilibrium position, the torque will disappear because the gravitational force will act straight down like this, um, it's not going to exert any torque about the point O, because as it should be clear to you by now, if a force passes through the reference point, if the line of action of the force passes through the reference point, then the torque is zero. But the pendulum is not going to stop at that point. It's going to keep swinging until it gets to the other side. And then once again, there will be a torque exerted by its weight. And so you're again going to have a restoring torque which tries to bring it back to its equilibrium position. And so the result of that is that the pendulum will just keep swinging back and forth along this arc. So that's an example of a restoring torque. So whenever you have any oscillating system, you have a restoring force or a restoring torque which repeatedly tries to bring the system back to its equilibrium position. But the system doesn't stop at its equilibrium position because of inertia, and it just and so the oscillation just continues. Okay. So any oscillating system is characterized by a restoring force or a restoring torque. If this restoring force or torque is proportional to the displacement, then the resulting motion is called a simple harmonic motion. So a simple harmonic motion is the simplest possible oscillation or the simplest possible periodic motion in which the restoring force or torque is directly proportional to the displacement. The restoring force is directly proportional to the displacement. The restoring torque is directly proportional to the angular displacement, theta. Then the motion is called a simple harmonic motion. What if the restoring force is not proportional to the displacement? In that case, you would have a periodic motion, but it would be a more complicated oscillation. And so that would be beyond the scope of this analysis. So we are only looking at restoring forces or torques which are proportional to the displacement. Okay, you can easily see that that is the case, at least in the first analysis that we did. So let's look at the restoring force in the case of the spring mass system. So when you displace the mass out to a distance x, then what is the force acting on the mass? Now let me just draw a separate one over here. So suppose you have your spring like this. This is x equals 0. Now suppose you've displaced the mass out to some x. Okay, what is the force? What is the restoring force? So you know from long time ago that the force exerted by a spring is given by Hooke's law, and the force F is equal to minus kx, right? So you can see that the restoring force here is just the Hooke's law force, and you can see right away that it is directly proportional to the amount of displacement. So this is an example of simple harmonic motion. What would not be an example of simple harmonic motion? Suppose you had a force which was characterized, suppose you have some really weird wonky spring which does not obey Hooke's law, right? So suppose for that weird spring, F is equal to, instead of being minus kx, it's minus kx to the power of 3, right? That would also cause oscillations because this is a restoring force, but it would not necessarily, those oscillations would be a little more complicated, and so we would not call them SHM. So this is not SHM, but it would definitely be oscillations because this would also be a restoring force. And what is a restoring force again? A force which tries to bring the system back towards equilibrium. So that's a restoring force, right? So this particular restoring force would not produce simple harmonic motion, though it would produce some kind of oscillations. This one will produce simple harmonic motion. Okay, all right. Now, we had looked at the example with the torque. You can prove that the torque produced by mg is going to be proportional to the angular displacement, theta. I'm going to, when we get to angular oscillations, I'm going to actually show that to you. So here also the restoring torque produced by mg, you can show that it's approximately proportional to um, some constant. I mean, or I can write it like this. It's approximately some constant times theta. This I'll show to you later on. So my point here is that since the torque is proportional to theta, this is also an example of simple harmonic motion. So whenever the restoring force or the restoring torque is proportional to the displacement for the force and the angular displacement for the torque, then we say that the motion is simple harmonic, and this should have a negative sign. The motion is simple harmonic motion. Okay. So let's continue analyzing. Okay, let me first see if I can show you the simulation. All right, so I would recommend playing around with the simulation a little bit yourself, and let's see if we can get it to work. Okay, so this is a simulation of a spring mass system, and you can see what's happening. So if you stretch the mass out to a certain x max, then there is a force, a restoring force, which pulls it towards x equals 0, and then the mass gets to x equals 0, overshoots, goes over to the other side, and then the force is acting in the opposite direction, and it brings it back to x equals 0, and the overshoot happens again, and this just keeps repeating. Okay, so please play around with this simulation a little bit. You can change the mass of the block, you can change the stiffness of the spring. What happens if we change the stiffness of the spring? So let's see if I can do it here. Let's make it 150 or something. Can you tell what the difference was by making the spring stiffer? Okay, so I'll let you play around with this just to get a feel for simple harmonic motion. What we're going to do now is analyze this particular situation, the spring mass situation, in a little more detail mathematically. All right, so let's apply Newton's second law. So we have our spring, which is connected to a mass, and let's call x equals 0 the relaxed position of the spring when it's not stretched or extended, stretched or compressed. Suppose I have pulled the mass to the right a little bit out to a distance x so that the spring is stretched. Right, so I'll just draw the stretched spring. So I've stretched the spring out so that the mass is at position x. So what is the force going to be on the mass? The force will simply be kx. I'll just call this the spring force, which will be pointed to the left because the spring is stretched, right? So let's apply Newton's second law. We know that the force on the mass is equal to minus kx from Hooke's law, right? And we know that force is equal to mass times acceleration. Now, instead of writing the acceleration as a, I'm going to write it as d2x dt squared. You know that that is the definition of acceleration. We learned this back in chapter 2, and that is equal to minus k times x. All right. Now, let's take a look at this equation. Or I'll do one step and then we'll stare at this equation. So we can write this as d2x dt squared is equal to minus k over mx. And just to make this a little nicer to look at, I'm going to define k over m equals, so I'm defining this, some constant which is omega squared. Now k over m is a positive quantity, so I can give it any name I want. So I'm just calling it the square of some constant omega, right? So let's plug that in, and so then we get d2x dt2, and if I move everything to the left side, plus omega square x is equal to 0. This is what we are getting from applying Newton's second law to this situation. Right? Okay, now it looks a little bit different from what we've done before when we studied Newton's second law in chapters 4 and 5. There what we would do is we would apply Newton's second law, force F net equals mass times acceleration, and we could find the acceleration from there. The acceleration would be constant, and then we would apply kinematics to find the final velocity of the object and everything. But one thing that's different in this analysis is that the acceleration is not constant. As you can see from this line, the acceleration depends on x. So it's not a constant acceleration, right? And the equation that we just got over here is a particular type of equation in math which you might or might not have encountered before. This is called a differential equation. And the reason that we got a differential equation is precisely because the acceleration is not constant. If the acceleration were constant, Newton's second law would have given us an algebraic equation, and we all know how to handle algebraic equations. But if the acceleration is not constant, the math gave us a different kind of equation, which is called a differential equation. Now, some of you might have seen differential equations before. Some of you might have never heard of differential equations before listening to this video. So I'm going to explain to you what a differential equation is very briefly. So a differential equation, so let's think about what a, so here I'm talking about what is a differential equation. So let's just remind ourselves, what is an algebraic equation? So an algebraic equation is just like something like this: x plus 5 is equal to 7. It's just a game of find the missing number. You're given a clue about a certain number, and from that clue you have to find the missing number, right? A differential equation is actually quite similar. A differential equation is a game of find the missing function. You remember functions from your elementary calculus class? So you have some missing function f of x, right? Or you might have a function like this. In our case, we are looking for a function x, which is a function of time. And you have to find that function. You're given a clue which involves the function and its derivatives, and most likely the value of the function at a particular point. From there, you have to identify what the function is. So let's look at the differential equation that we just got. Our differential equation says that if there's a certain function x of t, if you take two derivatives of that function, it's a bit of a pain to keep writing x of t all the time. So when I write x, I just mean x of t. So if you take two derivatives of that function and then add to that omega square, which is some constant, times the function, the answer that you get is 0. So that is what this differential equation is telling us. So find me this function x of t such that if I take two derivatives of the function and add omega square, which is some constant, times that same function, the result will be 0. Let's try some arbitrary function just to show that there is a certain function that's going to work, other functions are not going to work. So let's try something like, try solving this equation by, let's just make a choice. Let's say x of t is equal to t squared. Why not? So let's plug this in and see if this works. So d2 dt squared, the second derivative of t squared is what we're going to do, plus omega squared times t squared. Let's see if that gives us 0. So the first derivative of t squared is 2t, the second derivative of t squared is just 2, right? Plus omega squared times x is just t squared. Is that always guaranteed to be 0? Absolutely not. I mean, it might be 0. Will it ever be 0? No, it will never be 0 because t squared cannot be negative. So this won't work at all, as you can see. So it does not satisfy the equation. So this tells you, this just shows you that there is a there is a particular function x of t which satisfies the equation. So the function x of t that satisfies the differential equation is called, and this is just terminology, mathematical terminology, the solution of the differential equation. Okay, so if you're given a differential equation, the solution to the equation means the function that satisfies that differential equation. In other words, the function which if you plug into that differential equation, you will get a true statement. Okay, so what the math gave us in this case, what Newton's second law gave us was a differential equation, right? And let me write that down again. So this is what we got from Newton's second law, where omega squared we defined as k divided by m. All right, now how do you solve a differential equation? How do we find the solution to this particular differential equation? Now you might, if you don't have a lot of experience with differential equations, you might think that there is probably some algorithmic procedure. For algebraic equations, you can just solve the equation by just following a set of rules, just rearrange the equation and all that, and you can just get the answer without really using any brain power. You might think that there is a similar procedure for differential equations. As it turns out, there isn't. So there are some differential equations that you can solve following some algorithmic procedure, but the majority of differential equations, you really don't know how to solve them. So guessing a solution and checking whether it works is actually a very good strategy for solving differential equations, right? All right, so since this is not a math class, we are not going to talk about how we are going to solve this differential equation. We are going to jump straight to the solution of this differential equation. Okay. All right. And before I do that, I showed you this simulation over here, and I have a series of questions over here. I would highly recommend, I asked you to play around with the simulation. I would highly recommend having this set of questions in front of you and doing these activities. I usually assign these as a quiz on Brightspace, but since we don't have a lot of time, I didn't do it this time. I would highly recommend doing these activities. It probably won't take you more than 3 or 4 minutes, but it would give you a good sense of simple harmonic motion if you just work through these simple activities with the simulation. Okay. All right, so now let's move on to the solution to our differential equation. The solution turns out to be this particular function. Now, this is not the only solution that works. you can also have sine. So you can do cosine or sine. So x equals a sine of omega t plus phi would also work. Okay, so the solution of this particular differential equation, x as a function of time that works, is equal to some constant a multiplied by cosine or sine omega times t plus phi. As you can see, this is clearly a function of x, there a function of t, there is t in it, and there are three constants in this expression. One of them is a, one of them is omega, and the other one is phi. So these are the three constants of our equation, constants in this solution. Okay, now let's try to visualize what the solution looks like. And first of all, you can plug this. You can feel absolutely free to plug this into our differential equation and convince yourself that it does indeed satisfy it. So feel absolutely free to pause the video and check that this is indeed a solution to our differential equation. Okay, unlike the t-square that we tried earlier. All right, now let us visualize what this solution is telling us. Let's try to draw it graphically. So what does this function look like? A cosine omega t plus phi. It's going to be, you all know what a cosine function looks like. So it's going to be something like this. It's going to be sinusoidal. Okay. It's going to oscillate. The maximum value of cosine is +1 and the minimum value is -1. So since this is multiplied by a, the maximum value of the function is going to be plus a, and the minimum value of this function is going to be minus a. So x will keep on oscillating between plus a and minus a. Going back to the original example that we started with, we had a mass initially at x equals 0. So what we had done was we stretched out the mass to a certain length. Let's call the point where we stretch the mass out to as x equals a. So what the solution is telling us here is that the mass will oscillate between x equals plus a and x equals minus a. So it will just keep on oscillating between, and that's exactly what we expect it to do on physical grounds. So x will just oscillate between plus a and minus a, and a is called the amplitude of the simple harmonic motion. Okay, now on slide 5, I define a few terms for you. So we already talked about the amplitude. So that's the maximum magnitude of displacement on either side of the equilibrium position, which is x equals 0. The next term that we are going to define is the period of the oscillation. So what is period? Period is simply the time taken for one complete cycle. So you can start wherever you like. You can start at x equals 0. So one complete period would be when it goes to x equals plus a, comes back to x equals 0, that's half a period, goes to x equals minus a, and then comes back to x equals 0. And then the full cycle is complete, right? And it starts a new cycle. So the period is the time taken for one complete cycle. Okay, what about frequency? Frequency is the number of cycles per unit time. So if so the frequency is just how many cycles does it do per unit time. So suppose the system oscillates. So you're standing there with a stopwatch, and you count that in 10 seconds it oscillates 50 times. Right? So let's say that you could count really fast. In 10 seconds, you count 50 full cycles. Right? So in that case, that would mean that it's doing um, 5 cycles per second. And so that would be the frequency. So the frequency is the number of cycles per unit time. So if you're measuring time in seconds, then the frequency is sometimes called hertz. So number of cycles per unit time, that's the frequency. And the unit is hertz. Hertz just means 1 cycle per second. Cycle doesn't have any units, it's a pure number. So 1 hertz is 1 over seconds. Okay. All right. So coming back to our spring mass system again, suppose you just disturb the system, like you push it to one side or you just give it a whack and you just set it oscillating, then it's going to pick a certain frequency and it's just going to stick to that frequency, right? What is that frequency going to depend on? It depends on two things. It depends on how stiff the spring is. We are going to see that. And it also depends on the mass. So those are the two things that the frequency is going to depend on. But it will just pick that frequency and it will just oscillate at that frequency. Right? So this is sometimes called the natural frequency. So unless you are forcing the system to vibrate in some other way, like unless you're holding on to the mass and making it vibrate at a certain frequency, if you just let it go, if you just stretch the mass to one side and just stretch the spring pushing the mass to one side and just let it oscillate, it's going to just pick a certain frequency and it's always going to vibrate at that particular frequency. And that frequency is called the natural frequency of this particular system. All right. Now, in our equation over here, we had this quantity omega. Omega is called the angular frequency of oscillation. So what is this angular frequency? I think it's most convenient to just think of the angular frequency as a quantity that's related to the frequency of oscillation. So the angular frequency is just related to the frequency f that we just studied through the relationship that omega is equal to 2 pi times f. So what that means is that if you're given the omega, you can find the frequency of oscillation by just dividing it by 2 pi, right? And the frequency, hopefully you understand, is the number of oscillations per second. Omega is just another way of expressing the frequency. It's 2 pi multiplied by the frequency, right? Okay. Finally, there is this other constant here, the phi. So this is called the phase angle, or it's also called the phase constant or phase constant. What does that stand for? That is determined by where the system is, at what the x of the system is, and what the v of the system, what the displacement and velocity of the system are at t equals 0. So the phi, the phase angle, is a constant that's determined by the initial position and velocity of the system. So those are all the constants that we are going to encounter. Now, there is a relationship between omega and f, which we already talked about. It's right here. There is also a relationship between frequency and time period. So let's just quickly review what time period and frequency are. So I already told you what time period is. It's the time taken for one complete cycle, and frequency is the number of cycles per unit time. So can you figure out the relationship between them? It's really simple. Suppose I tell you that the system is doing 5 cycles uh, per second, right? So the frequency of the system, frequency of a certain oscillating system, f is equal to 5 hertz, which just means 5 cycles per second. Can you figure out the time period from that? Of course, if it's doing 5 cycles in 1 second, that means one cycle is happening in 1/5 of a second. So the time period would just be 1/5 of a second, right? So you can clearly see that frequency and time period satisfy this relationship f equals 1 over t, or t equals 1 over f. So that's the relationship between frequency and time period. All right. Okay. Now we have found, so what we did so far is we applied Newton's second law to the spring mass system, and Newton's second law gave us a differential equation, which I'll just write down here again. And we solved this differential equation and we got the solution. X of t is equal to a cosine or sine omega t plus 5, right? This solution, another name for it is also called the equation of motion of the system. That's just a name for the solution. All right, let's just make sure that we are clear about what this equation of motion is doing for us. So we have our spring mass system. Let's say that this is x equals 0. The mass is not necessarily over here. Let's say the mass is somewhere over here at some x. So what this equation of motion is doing for us is that you can plug in, you can choose any t you want, right? So let's say at t equals 7, you can plug that into our x of t, and you presumably know the values of the constants a, omega, and phi. You will know what x is at t equals 7. So what this equation is doing for you is that it's fully specifying the motion at any time t, which means that you know everything about the motion once you have this equation. You know its position at any time t. You can also differentiate this expression and get an expression for the velocity at any time t, and also the acceleration at any time t, right? So this equation of motion fully solves the problem of the simple harmonic oscillator by completely specifying the position of the simple harmonic oscillator at which in this case the position of the mass at any time t, right? So hopefully that's clear what this did for us. Okay, so now let's go ahead and find expressions for the velocity. So we know we know how to find the velocity if you know x as a function of time. This is stuff that we've done a long time ago. Velocity is just dx dt, right? So let's go ahead and take a derivative. So when you take a derivative of cosine, you get negative sine, and if you apply the chain rule in taking derivatives, then the omega is going to come out. So please review derivatives if you've forgotten. So if you take a dx dt, you're going to get minus a omega sine omega t plus phi, right? And so that's our expression for velocity. And you can take one more derivative to get the acceleration. That would, if you differentiate this one more time, you would get minus a, another factor of omega will be pulled out. So minus omega squared a cosine omega t plus phi, right? Now let's look at this expression, minus omega squared a cosine omega t plus phi. Maybe I can just write it in a slightly more suggestive way. Okay. Now, does this ring any bells at all? Minus omega squared a cosine omega t plus phi. What does the a cosine omega t plus phi remind you of? This is just x as a function of t, right? So I can write a or d2x dt square as minus omega squared times x, right? And look at this. So what I got over here is d2x dt square with this particular x is equal to minus omega square x, or in other words, with this particular x, d2x dt squared plus omega square x is equal to 0. So I've verified that our function x of t satisfies the original differential equation, right? So, okay, so what we saw here is that x of t that we have chosen satisfies the original differential equation. All right. So that's a nice aside of side benefit of doing this. We wanted to find the velocity and the acceleration, and in finding the acceleration, we also the function does satisfy the differential equation. The function x of t does satisfy the original differential equation. All right, now we have found the velocity and the acceleration, and I'll just write the acceleration like this: a of t is equal to minus omega squared x. Both of these are functions of time, right? But sometimes it's more convenient to express the velocity not as a function of time. So we found the velocity as a function of time, but we want to express it as a function of x rather than a velocity rather than a function of time. So here it's a function of t. We want to express that as a function of x, because a problem might say that a simple harmonic oscillator in a spring mass system, what is the velocity of the mass when it's out at a distance x equals 0.7 meters, rather than asking you what is the velocity when t equals 25 seconds. That you could just plug in to v of t and find the velocity, but it might say what is the velocity when x equals something, right? So let's just derive an expression for the velocity as a function of x. So that's not hard to do at all. The way you would do that is you could just take the expression for v of t and square it. So let's do that. So this is what we're going to try to do now. So we have v of t is equal to minus omega a sine omega t plus phi. Let's start with that. Let's square this. So v square is equal to plus omega square a square sine square omega t plus phi. Okay, now I'm going to use the identity that sine square plus cosine square of anything is equal to 1, right? So I can write the sine square as 1 minus cosine square. So I can write this as omega square a square 1 minus cosine square omega t plus phi. So that's exactly what we have. And then we can do v square is equal to omega square a square minus omega square a square cosine square omega t plus phi. Omega t plus phi. All right. Okay. Now, what does this remind you of, this part? This is just x squared, right? Because x is a cosine omega t plus phi. So we can plug that in and get v square is equal to omega square a square minus omega square x square. And if I just factor out the omega, and then if I take a square root of both sides, I get v is equal to plus minus, because I'm taking a square root, omega square root of a squared minus x squared, right? And this is the expression. This is exactly what I was looking for. So this is telling me that at a certain x, so in this expression, this is my v of x that I was looking for. So I can plug in any x I want, and it gives me the velocity that the particle has at that particular x. Why am I getting a plus or minus? So let's think back to the spring mass system again. So when the mass is somewhere, this is, let's say this is x equals 0. Um, I'll just do it like this. Let's say that this is x equals 0 and this mass is somewhere over here, let's say, and this is x equals a. So when the mass is at some x, I'm asking what velocity it has. Now, it could be moving to the right when it's at x, or it could also be on its way back and it could be moving to the left. And that's why it could have both of these velocities. And that's why the math is giving us a plus minus sign, because the velocity could be either to the right or to the left when it's at this particular x. All right. Now, you might remember seeing this expression a long, long time ago when we talked about the work kinetic energy theorem. And so we had derived this expression using conservation of energy at that time. Okay, and I told you that nobody is going to remember this when we get to simple harmonic motion, and I was probably correct. Okay. One thing we can see from this expression is we can find out what is the maximum velocity that the simple harmonic oscillator is going to have. So Vmax, the maximum velocity that the mass ever has, happens when, by just looking at the mathematical structure of this expression, how can you make it as large as it possibly can be? So you know that this expression will reach its maximum value when you can just get rid of this x squared, because x squared is subtracting from a squared, right? And so that's diminishing the value of the expression. So if you could just make this x squared go away, then the expression will reach its maximum value, right? And so that tells you that the maximum value of this expression is omega times a, and that happens when x is equal to 0. So the maximum speed of the mass is going to be when it is at x equals 0. That's when it will be moving at the fastest, right? When will its velocity be 0? The velocity, see if you can answer this question without doing the math. So so the mass is oscillating back and forth between x equals plus a and x equals minus a. So where exactly will its velocity be 0, do you think? The answer is, the velocity is obviously going to be 0 at x equals plus a and x equals minus a. Let's say x equals minus a is over here. So the velocity will be 0 at the two turning points, right? And you can also see that from our expression for velocity. If you plug in x equals plus a or minus a into our expression for velocity, you get v equals 0. So v is equal to 0 at the turning points x equals plus a or x equals minus a. All right. There is one more thing that we can talk about, which is the energy of a simple harmonic oscillator. So the energy of the simple harmonic oscillator, the spring mass system, is going to be, it's going to have two types of energy. It's going to have kinetic energy of the mass that's moving. It will also have potential energy because the spring is stretched or compressed, right? So the total energy is going to be half mv squared, which is the kinetic energy of the mass, plus half kx squared, which is the potential energy of the spring, right? And so this is the total energy. Now, this total energy is constant, okay? Because you know that it's constant because there is no, we are ignoring friction. So the only force here is a conservative force, the spring force. And so if the only forces are conservative, then the total energy, the sum of the kinetic plus potential energy, will remain constant. You can also see this graphically if you just look at this graph. So the potential energy is given by half kx squared. So that's going to look like a parabola if you plot that. So this is the u equals half kx squared. So the red parabola is a graph of the potential energy versus x. The total energy will remain constant. That's this horizontal green line, right? And so the kinetic energy will just be the difference between the total energy and the potential energy. So for example, over here, the potential energy is this point on the graph, and the total energy is this point on the graph, and so the kinetic energy is just the difference between those two. So you can see that as the mass oscillates back and forth, it's the amount of kinetic energy and potential energy that it has keep changing, but the sum of the kinetic and the potential energies is constant. When the mass is at x equals 0, its potential energy is 0, right? Because the spring is not stretched at that point. So its entire energy is kinetic, and that is why. So you can see that the total energy is equal to the kinetic energy at this point. So that explains why the velocity is the highest, because the kinetic energy reaches a maximum at that point. And when the mass is at one of these two turning points over here and over here, then the potential energy is, then the kinetic energy is 0, because it's reached the end point, it's turning around, it's paused for a moment, so its velocity is 0. So the entire energy is potential. And so the potential energy at these turning points is given by half ka square. And so that is also equal to the total energy. So the total energy is half ka square, right? And another expression for the total energy, you can derive that from the fact that the total energy is kinetic at x equals 0 is, I'll just do it over here. So at x equals 0, the total energy is kinetic, as you can see from the graph. So the total energy is equal to half m. What velocity does it have at x equals 0? The velocity is Vmax, which we just derived. So the total energy would be half m Vmax square. And we just derived an expression for Vmax in the previous slide. Vmax is omega times A. So let's plug that in. I'll just work over here. I'm running out of space. So this is the energy at any point. And what we saw was, what we are doing now is we are calculating the energy at x equals 0, right? So we know that V is equal to Vmax, which we just derived is omega times A, right? So the total energy would be 1/2 m Vmax square at x equals 0. There is no potential energy, it's all kinetic energy. And if we plug in 1/2 m, if we plug in the Vmax, which is omega A, we get omega squared A square, right? And so what is m times omega square? Omega square is defined as k divided by m. So m omega square is just k, so we get half ka square. So half ka square is the total energy of the simple harmonic oscillator. You can see that either by plugging in, finding the total energy at x equals 0, or more directly, if you find the total energy at x equals plus minus a, at x equals plus minus a, the velocity is 0, so the total energy is potential. So in that case, it would just be E equals half k a square, because V is equal to 0. So there's no kinetic energy, and you get the same thing again. So the total energy of the simple harmonic oscillator is just given by half ka square. And in general, at any arbitrary point, it's going to be half mv square plus half kx square. Okay, so we found the total energy of the simple harmonic oscillator. All right,